Hey everyone, so today we are going to talk about comparison tests for improper integral, or you can say the test of convergence for improper integral. So there are two tests of convergence, one is direct comparison test and one is limit comparison test for improper integrals. So today we are only going to concentrate on direct comparison test for both type 1 as well as type 2 because I am going to take some 4-5 examples. So I don't want to make a lecture very big, so that's why one by one. Okay, so today we'll concentrate on direct comparison test. Now why do we need this test for convergence? See, integrals are not always easy to solve. Okay, suppose if I give you integral 1 to infinity e raised to minus x square dx. Now this is non-elementary, you cannot solve this integral. But then if I know the nature of that integral, nature as in whether it is a convergent integral or a divergent integral. If it's divergent, it's okay. But if it's convergent integral and if I cannot solve it by normal method, but even if I know it's convergent, then I can use the techniques from numerical methods to find its approximate value. Okay, so knowing whether it is convergent or not, if it's convergent, we can use those numerical methods to find the approximate value. Okay, so that's why it's good if we know the nature, if we can't solve it directly. So in that view, the first one is the direct comparison test. So what do you do over here? If you have a function which is difficult to integrate, you try to compare that function with a simpler function whose nature you know, and from that you try to conclude the nature of the given integral. So now for example, in this your function is what? E raised to minus x square. Now you want to compare with some other function. Now question is how to find that other function. Okay, so it's not that trivial. It's not there is no some rule or something. Okay, so if you want to find some other function, what you can do is, like if you have a square or something power, so what you can do is whenever you have a power in a function, you try to ignore the power and see what is left. Okay, if you have the constants in the function, then you ignore the constants and see what is left. You try to compare with that function. If you have some trigonometry in the integral, then you ignore those trigonometric functions and see what is left. If there is some log or exponential, then you try to ignore that and see what is left and then try to compare your function. So these are the tricks which will help you many times, not always, but 99% keeping these tricks will always help you. Okay, to guess the new function. Now here I can see there is a power over here. So if I ignore this power, what I get e raised to minus x. So what is this? This is my g of x. So I'm using that first thing. There was a power, so I ignore the power. I'm not using the last one, exponential, because if I ignore exponential, nothing is left. Okay, so yeah, so that's why I'm having this as a function. Now you try to compare them. So how to compare? Now if you observe, so you start with the polynomial x and x square. So I know that x is always less than x square, less equal x square on the domain 1 to infinity, because I'm taking the square. So obviously this is bigger. Now if I multiply by minus sign, so minus x and minus x square, obviously the inequality will reverse because I am multiplying by minus sign. Now if I take exponential on both sides, e raised to minus x and e raised to minus x square, what will happen to inequality? Will it remain same or it will change? It will remain same. Why? Because the exponential is an increasing function. Why? Because the derivative of exponential is exponential itself, and exponential is always positive. And for increasing function, the inequality remains the same. So what do I have is, I have my f is less equal g. My f is less equal g. Okay, so that's the relation between f and g. Now what about g? Can you say anything about g? Yes, if I ask you what is integral 1 to infinity e raised to minus x dx, well, this comes out to be a finite number. It comes out to be 1 by e. I have solved in my earlier lecture on improper integral of type 1. So if you see that lecture, I have solved that problem over here. So f is less than g and integral of g is finite. This integral is finite. So therefore this integral also has to be finite, right? So if my f is less equal g, one can keep in mind that since my f is less equal g, my integral of f is less equal integral of g. So therefore integral of f is less equal, this is some finite number 1 by e. So can this be infinite? No, right? Because this is less than a finite number. Can this be infinite? No. Why? Because your function is positive, domain is positive, so this can't be negative. So this is definitely greater or equal 0, and it is less equal a finite number. Therefore this has to be a finite number, and therefore this integral converges. Okay, so you are comparing your function with another function, with another simpler function, and then you are finding that integral to conclude about the integral of your given function. So since here we are comparing directly two functions, therefore this test is called as a direct comparison test. So now let me give you a statement, and then we will see some 5-6 different kind of examples. So here is a statement. So I have stated for type 1, similar theorem is there for type 2 as well. Okay, once we see examples, this will be more clear. So it says that if you have two continuous function on this domain, and they are what? Both are positive functions, greater or equal 0, and one is less than the other for all x in this interval. Okay, so you need positive functions, both of them should be positive and both of them should be continuous. Okay, and you have a relation between them, greater equal or less equal. Then what the theorem says, if the integral of the bigger function converges, if the integral of the bigger function converges, so this is a finite number, this integral is finite. So what can you say about this integral? Then integral a to infinity f of x dx also converges, right? So if the bigger integral converges, that means this is a finite number, integral of this. Therefore the integral of this also has to be finite. Okay, and the second statement is, if the smaller integral diverges, that means integral of the smaller function diverges, means if this is infinite, what can you say about integral of this? Now integral of this is greater than integral of this. Now this is infinite, so therefore this also has to be infinite. So then integral a to infinity g of x dx diverges. So that's the statement. Now don't learn this theorem in terms of f and g. How you will learn this theorem? So one function is less than another function. Now if this integral diverges, smaller one, then obviously bigger integral also diverges, because this is bigger than this. So if the smaller diverges, bigger also diverges. If the bigger converges, then obviously this is less than this. So if the bigger converges, then smaller also converges. And that's what I have written over here. Now another point to observe here is, see, if this is convergent, if integral f is convergent, then you can't say anything about integral g, because if this integral is finite, this is greater than a finite number. So this can be infinite or this can be finite. Okay, so if the smaller is convergent, you can't say anything about the bigger one. Okay, and second is, if the bigger one is divergent, if this integral is infinite, this is less than infinite, so this can be infinite or this can be a number. Okay, so if the bigger one is infinite, if the bigger integral diverges, you can't say about the smaller integral. Okay, so these are the 2 points one has to be careful of. Okay, so if the bigger converges, smaller converges. If the smaller diverges, bigger also diverges. So that's the theorem. Now let's go for examples. So here is the first example. You need to tell the behavior or the nature of this integral. So what is your function? The first step is you should always write down your function. Okay, good. What is the domain? 1 to infinity. Now question is, what function you will choose? Another function. So as I told you, as you can see, there is a constant over here, x square plus 1. So you can simply ignore the constant and now try to play with this. If this gives you the answer, well and good. If this doesn't give you the answer, then you need to modify it further. Okay, but let's go one by one. Let's see that if eliminating constant will help you or not. Okay, so now, okay, if this is my f and g, are f and g continuous? Yes, because numerator is continuous, denominator is continuous. Denominator is never 0 over this interval. So ratio of two continuous function is continuous, and therefore f and g, they are continuous on 1 comma infinity. Whatever argument I told, I am not writing, otherwise it will take a lot of time. So yeah, ratio of two continuous function is continuous because the numerator is continuous, denominator is continuous, denominator is never 0. So your f and g are continuous. Okay, are they positive? Yes, because numerator denominator both are positive. So your f and g both are positive functions. Good. Now compare f and g, which one is bigger, which one is smaller. Now as you can see, your x square is less than x square plus 1 because you are adding something to this. So when you take the reciprocal, inequality changes. Okay, when you take the reciprocal, inequality changes. So what you can see, your g is bigger than f, or you can say, so your 0 less equal f is less equal g, your f is less than g. Okay, so I got the connection between f and g, and your f and g are satisfying the conditions of direct comparison test. Good. Now I want to find the nature of integral of f. So let's try to find the nature of integral of g. What can you say about this integral? Does this converge or diverge? This converges thanks to our p integral test. So if you recall your p integral test, I have talked about this in my improper integral of type 1. So your p is 2, which is bigger than 1, therefore this integral converges. So your given integral is less than integral of g, and integral of g is converging, therefore by dct your integral of f also converges. So that's how comparing this with some nice function whose nature you know help us to determine the nature of the given integral. Okay, let's go for the second one. So you have minus infinity to infinity dx upon root of x raised to 4 plus 1. Now here you can say your function is an even function because what is your f of x over here? Your f of x is 1 upon square root of x raised to 4 plus 1. And what will be your f of minus x? 1 upon root of minus x raised to 4, which is again x raised to 4, right? So your function is an even function. So whenever your function is an even function, and when you have minus a to a, so here also this will be integral 2 times integral 0 to infinity dx upon root of x raised to 4 plus 1. That's just one observation one can see. Okay, so now let's check the nature of this. Okay, so this is my f. What g function you will choose? So as I said earlier, there is a constant. Ignore constant. So what is left? 1 upon root of x raised to 4. But what is root of x raised to 4? It is x square. Okay, good. So we have this g function. Now let's try to play with this f and g. Are they positive? Yes. Domain is 0 to infinity and both are positive. But the problem here is I can't take this g as my function. Why? Because this is not defined at 0. Okay, so then what to do for this? So I can't apply my p integral test, right? I can't say integral 0 to infinity 1 upon x square dx converges by p integral test, because this is from a to infinity where a has to be positive. So I need to do little bit of modification. So now what will I do? Now 0 is creating the problem, right? So what you do is you write this integral. So let me erase this. So what I will do is, this is 2 times, this is 0 to 1 f of x dx plus 1 to infinity f of x dx. That's the smart work I am doing. Okay, f is what? This 1 upon this. Okay, now does this integral exist? Yes. Why? Because the domain is bounded. What is the function? 1 upon root of x raised to 4 plus 1. Is the function continuous? Yes. Numerator is continuous, denominator is continuous. It's never 0 over this interval. So your function is continuous over closed and bounded domain. So thanks to Riemann theorem, this integral exists. I don't know what the value is, but I know that this integral exists. Okay, good. So now I have to only worry about this function over this domain. So that's how I get rid of 0. Okay, so now, now you have to see which one is bigger. Okay, now you can see that root of x raised to 4 plus 1 is, and I have root of x raised to 4. Which one is bigger? This one is bigger because I am having plus 1. So 1 upon root x raised to 4 plus 1 is less than 1 upon root of x4 is nothing but x square. So what and they are greater than 0. So I have 0 less than f less than g. So they are positive function and both are continuous over the domain, and your f and g, they are continuous over 1 comma infinity. So all the conditions of DCT are satisfied. And what can you say about integral 1 to infinity g of x dx, it converges by p integral test. So this is convergent by p integral test because your p is 2 which is bigger than 1, and therefore by dct integral 1 to infinity f dx converges. So this converges by p integral test, and by dct this integral also converges. So therefore what we get, this also exists. I don't know what is the value, but this is converging, this is converging. So both are going towards the finite number, so their addition will also go towards the finite number, and therefore this integral converges. So that's how you have to do this smart thing and some very good theorem of Riemann to solve this kind of problems. Okay, let's go for the next one. So here also you need to determine the nature, but you will see that this is type 2 integral, but it's okay, dct is applied for type 2 as well, same thing happens here as well. Okay, so what is your function over here? Your function over here is 1 upon root x plus sin x. Okay, and the domain is 0 to pi. Why this is improper integral of type 2? As you can see, this function is discontinuous at 0. Okay, so therefore this is of type 2, not type 1, because the domain is bounded, so not of type 1. Okay, so this is my function. Now what function should I choose? That's the question. So as I told you at the start, you can see trigonometry is over here. So ignore trigonometry and see what you get. You get 1 upon root x. And try to compare this f and g. Now you can see which one is bigger, root x plus sin x and root x. Now from 0 to pi, you know this is the graph for sin x. That means what, it is positive. So this is always positive. So this is greater equal. And now when I take the reciprocal, I have 1 upon root of x plus sin x is less equal 1 upon root x. When you take the reciprocal, inequality changes. So what do I have? F is less equal g. Okay, good. So I have f is less equal g. Both are positive function. Yes, they are positive function. You can ignore the problematic point. Okay, so if you ignore the problematic point, both are positive functions. Good. Okay. Even at problematic, actually it is not defined, and if you want to take it as plus infinity, so again is positive. You ignore the problematic point. Okay, so I have this thing. Are they continuous except the problematic point? Yes, they are continuous except at the problematic point. Good. Now you apply dct. So what do you know about integral 0 to pi dx upon root x means x raised to half. Now don't be in a hurry and say this is convergent, this is divergent by p integral test. For p integral you need infinite, a to infinity. Okay, so don't do that mistake. Now this is the improper integral of type 2. You know how to solve the improper integral of type 2. 0 is the problematic point. So you remove your problematic point and then you take limit c going to 0 minus. What is this? This is 2 root x. Limit c approaching to 0 minus 2 root x. That means 2 root pi minus root c. And as c goes to 0, this is 2 root pi, which is a finite number. So your f is less equal g. Integral of g is finite. Therefore, by direct comparison test, your integral f is also finite. That means integral of this function is convergent. So this integral converges. So here are 3 homework problems for you. So 0 to 1 dt upon t minus sin t. So you can see trigonometry. So ignore trigonometry, you will have 1 upon t. Try to compare and see what is the answer. Here also you can see exponential. So there is no power, there is no constant, there is no trigonometry, but yeah, there is exponential. So ignore exponential and you have 1 upon x. Try to see what you get. And here also you can see it's an even function. And yeah, so your job is to tell me the answer, the nature for these 3 integrals. If you have any other question, that also you can ask me in the comment section. And if everything is clear, then yes, do not forget to like, share and subscribe. Thank you.